Cool. I guess I'll get started.
All right.
Awesome.
Yeah. Thank you, Michael. Um, yeah. Yeah. We will now begin the second half of the tooling talk.
Awesome. 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 Cool. So the title is building a significantly better data store for IPLD blockchain data, and part of the idea of better is better than what, and what are we comparing to? So what we currently use, at least in Lotus, is a key value data store called Badger. And so what I've been working on as a side project, hobby even, and initially it was to give myself something to get more experience with Go as I was more getting new to Go. And a lot under the hood of what we'll be talking about uses memory mapped files and uses pointers in a way that Go doesn't traditionally like. So part of the fun was learning a bit about that and how to make things work. And so here's an outline of what we'll be covering. And so the first thing that we'll go over is log structured merged file databases or key value stores. And Badger, which is currently embedded inside of Lotus, uses the LSM structure or format or algorithm in order to do its key value store. And we're going to talk a bit about that, why it's good, why it's not good, where it fails, to be the right data store for more key value hash-based IPLD data. I'll go over a bit, how does a hash map generally work in common use cases? What is hard about having a hash map be persistent such that it's stored on disk and not just an in-memory data structure? Then we'll go into the project that I'll be sharing about, calling it GoMap for now. Probably needs a better name and would love later for suggestions. But more to the point, this was somewhat initially a hobby and learning project that I'm looking now to upscale, polish, get more eyes on, get collaborators, and extend out. There's a fun way of sharding these hash maps to optimize for multi-core systems. I'll show you results comparing this GoMap project with Badger and kind of next steps. Cool, so here we go. What is a log structured merge file, LSM? Log structured merge, yeah, that's hard. Another advantage of hashmap is it's a bit easier to say. And so I have a few of these, and what's important about the log structured merge file is that there's different layers. And the idea is that there's a fast layer that writes initially land on. That's the in-memory layer. And over time, data gets garbage collected, compacted, and put into multiple layers. LSMs are optimized for writes. You're, in a way, appending to a file as you collect data. But reads are more complicated because you need to go through all these different tiers. This illustrates how on one set on top, we have some data in disk and some data in memory, and then some of the in-memory data is flushed into disk. Because LSMs work with sorted data, you can merge sort one already sorted set with another already sorted set in a linear time just by sweeping down. It's like combining two phone books. So there are advantages in general with an LSM. And then here, this talk goes into more detail about, in practice, how LSMs work. And what you see here more so are these different layers and levels that the tree uses. So it's a tree of trees, or however many trees we have here. And importantly, the compaction takes data from the mem table into level 0, into level 1, into level 2, and there's algorithms that specify how these grow, how often it's compacted. But notably, there's a lot of write amplification. So data is written into the mem table, that gets full, it gets written into level 0, it gets written into level 1. There's a lot of write amplification, and the trade-off, again, is for fast writes into the mem table and then flushing and reasonably fast reads. Great. So in contrast to that, with a hash table, hash tables are much more read optimized. If you are checking for a value in the key value store and it's not in the data store, you have to check the mem table, not find it. You have to check level 0, not find it, check level 1, and check level 2. So before we go into the GoMap project that I want to share and get support with and feedback on, first, just want to dive into hash maps and how they generally work. It seems like all the examples love using a phone book, which is fun. So we have John Smith, and we have their phone number, this person, etc. So this is sort of the most simple version where you hash something and you have this bucket where this bucket is essentially all these phone numbers in this example are fixed number of digits, fixed number of bytes. So it's really easy to pre-allocate essentially an array of whatever 8 bytes is here or so. And then this super simple algorithm takes this string, hashes it, divides it by, I guess here would be 16, mod 16, and then sees, okay, this hash, blah, 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 so here we go. Just for this example, there's no idea of how to rectify hash collisions. So if your hash algorithm, Lisa and John Smith both hash to the same bucket, there's something more complicated that we have to do. And so that's sort of this open addressing, linear probing type of example. And so what's changed in this example is we're also keeping the key in the data that we store. So just as a reminder here, in the data we're actually storing, there's just phone numbers, and then we're using the hash to find it. There's really cool algorithms called perfect hashing, where you can take a fixed set of data and I algorithmically identify a hashing function such that for that fixed set, you don't have any collisions. So if you have a fixed set of data, there's really cool, really optimized things that you can do. But what we do in this case, and what GoMap does, is in this example, John and Sandra both hash to this same 873 index. And so it's just a first come, first serve. John gets the first entry, Sandra gets the entry after that. And then when we're checking, does John Smith or does Sandra have a phone number in our database? What we do is we hash Sandra, we get to 873, we check the key, we see that's not their name, and then we go to the next one and go to the next one until we either find them or find an empty row. And then there's fun algorithmic things you need to do where when this is empty, you always find a new blank place. And as it gets more and more full, the number of sequential hops that you have to check gets higher and higher. And there's this magic number around 2/3 where once you get to 2/3, the performance starts deviating and degrading. And so we will do what's called a resize. And we'll maybe get into that or maybe not. It's a little more complicated. So this is a little more accurate in terms of how the project works. So what's different here is that we have pointers. So here we just have, okay, we're maybe allocating 32 bytes for the person's name, fixed size. We're allocating a fixed size for the phone number. And there's just this one coherent on disk or memory data structure. And then here instead we have this bucket system where we either have something indicating that the data is empty, or we have a pointer indicating into another table how to find this result. So when we add and get and check data, what we want to do is hash our key, find what bucket we land on, and then sequentially probe, does this key match the key that we're looking at? And if so, great, here's the name and phone number of the person, and the same rules before apply with empty. And I think this diagram is a little different, a little more complicated, but we're using in GoMap this idea of open addressing and linear probing. So that all works great if all your data is in memory. You have the malloc allocator, you have the Golang allocator, you have Python, and it's easy to create pointers for your data, store these pointers, and then know that those pointers will still have your data. If we're storing data on the disk, we need something a little bit different. And so what we want to do is replicate something like this using disk, so that if we restart Lotus, we don't lose all of our data. And so what we do instead, what I do instead is create this data structure, very, very similar. So here I'm talking about this bucket idea. So this is an array of fixed size, and what we have in it is this struct, and we have the hash of the key, and we could do without that, but it really helps our performance, where we don't have to dereference or reference from our pointers, but also we have this thing that's I'm calling slab offset, and that's basically creating a simple allocation system using a file. So instead of having a pointer that gives us an address in memory, we're creating a pointer that just gives us an offset into a file where our keys and values are stored and serialized in a, right now, pretty straightforward way, where we have the key size, the value size, and the key and the value on disk. So now going into, so taking that idea where we take a hash map where we generally want things, where this idea of pointers generally stops hash maps from working on disk because of the persistence and all of that, using a simple slab allocation file, we can now start to move from an in-memory system into an on-disk system. And one important kind of thing to call out basically is that this hash index is memory mapped and is in memory and will need to be memory and in memory for things to be fast. And then this area where we have the entries is on disk, and we will use disk IO in order to save this so that we can create really fast and data on disk and access it using an in-memory index. So really simply just starting now to go into GoMap. And again, if this is the URL of it. So I'm going to give a quick walkthrough to how do we add data into this system. And basically, before we add data, what we want to do is just see if it's there or not. So first, we're going to talk about how do we get data. And more or less, this nicely simple, small function takes what we were looking at in the last couple slides, takes our key, takes the hash of our key. There's more we can say about that, but given the key, it gives us an index into our hash array. And then we check, is there a value here? If not, okay, it's not in the data store, we can move on. And this is in contrast to the LSM where we have to check all the different layers in order to find the data. And then if there is data, we have to do the same thing in the other example. We have to check, well, is this the right data or is this just a hash collision? And that loop just continues until you either find your data or find an empty index or an empty struct in this array. So I think I'm hit. Okay, cool. So now how do we add data? So to add data, we first want to add it to the on-disk data slab. And so this is the most simple algorithm that we can do for that. And we take our key, we take our value, we have the initial offset, which is where we've been writing into our file. We write a uint64 that represents the length of our key. We write a uint64 that represents the length of our value. Then we write our key and we write our value. So this is how we go from sort of this pointer or slab index into actually the data that we care about. And at some point I had a var_int, variable int encoding function here to save a little bit of disk space, and definitely something I'll show the list of next steps, something I can bring back, an optimization that we can use, but not a big deal, didn't really move the needle that much, but still helpful and still a nice to have. But this kind of gives us one example of how we can have essentially a pointer system for memory allocation, but on disk. Cool. So some initial results to go into, and kind of comparing first this one and this one, and these are just kind of shooting from the hip what happens when we take Lotus, replace Badger with this GoMap project, and import our chain and ask the chain to halt. And excitingly, we're beating the database that should be write optimized and is less read optimized on write speed. 7 minutes versus 13 minutes. And comparing things a bit further, I just ran these two as a benchmark, go-bench or whatever the Go benchmark built in is, and Badger was giving me 9,000 nanoseconds per operation, and this project's giving me 4,000. Now, that's awesome, and also we can maybe think about closing in on this and start figuring out what's slow about GoMap and how to optimize it further. But it's also nice to know that we're targeting built-in Go data structures that are pure memory. And I think that I'm hashing things a few extra times. There's things that we can figure out and optimize further. Cool. So an extra idea here that is pretty fun, and only putting this code on because this is the whole feature set is just in this. But it's the idea of, because we have a hash-based data store, we can do hash-based sharding. So we can take our one table and actually think of it as maybe number of CPU tables. And all we do here is, for each of those, we create a new GoMap hashmap And then when we do a write, we take our hashing function and use that to figure out which of these shards we want to write into. And when we do a read, we do the same thing. And so this is another way that we can get further speed ups. It would be as if we had a Badger installation for each, maybe for each CPU, and then did a hash and shard analysis on each key. Maybe as I'm saying this out loud, something to try out after this is what if we have number of CPU of Badgers? Does that make things faster? Does that make things slower? Does that use more memory, less? But the idea with that would be that Badger has a logarithmic growth pattern. And so here at least we can shard it a bit so that we kind of get ahead of the big O notation in a constant way. Cool. So sort of like next steps, where are we? What's kind of the idea? So one is just overall cleanup of the code base. I was reviewing it earlier today, and it's like, to do when you do an insert just out of convenience, hashing the key at least one extra time, just to didn't bother passing the pre-computed hash around. So that was one thing that I saw. But also now that the general structure of what data goes where has settled, I can start to rethink and look at other implementations and come up with, okay, does this data structure make sense the way it's named, or can I kind of clean things up a bit? Then there's a few further optimizations. This is one I was starting to allude to. With Lotus, with IPLD data, the key already is a hash. So even more optimized would be, well, why hash the key? Why create a hash of a hash if all we need to do is distribute data into this bucket? So having a version of the Go map that just uses the key and uses basically an identity function for the hash function will speed things up a bit, and maybe might even be better than in terms of the hash functions in terms of using a better hashing function. Another idea is that all the way back here, I'm using uint64s. And so these are all in memory. And so depending on how many keys you have, pending resizes, you're using 16 bytes. So there's that much memory is needed per key. It's possible to make either of these uint32s, make this a bit smaller. The hashing function, it's pretty straightforward to make it a 32-bit int instead of a 64-bit int. And if you're taking the key, you can just take the first 4 bytes and use that. And for the slab offset, or kind of pointer allocation, we can chunk out the data so that instead of being able to offset any number into our file, maybe we have 64-byte chunks or 256-byte chunks. And then the idea there is that you're trading off memory efficiency for how fragmented your data is on disk. So potentially worth doing. Potentially the users of this are happy to throw an extra 16, 32, whatever gigabytes of RAM on their computer. So all depends. I think that I talk here about how it would be great to have different modes for this. So having a low memory mode where on one hand, great, we're dropping down to 32-bit ints, but also what we can do, and sorry for the whiplash going between all these slides, what we can do is take this hash and actually move it into the slab. So by having the hash in memory, it means that once we hash our key and check our in-memory index for if this key is right or not, because of this algorithm with collisions, it's much faster if the hash is in memory so that we can see, it's not, we got Sandra, not John. But if we wanted to, we could push that into disk and then only have 132-bit int per entry, which would keep things a lot smaller. I'm so almost done and would love your questions then. Thanks so much. There's a resize feature that I was working on where currently synchronously doing a resize. It works because it's very fast, but it would be nice to find the bug that I have in the async resize branch and fix that and merge that in. Also, we don't support deletes at all at this moment, and there's lots of different ways to do that in hash maps. Be nice to add more granular locking and consider if that's necessary, if that speeds things up or not. And then in terms of how things connect into Lotus, and this is a little more long-term thinking, it would be great to take some of the ideas of what we're having in SplitStore and implement actual reference counting natively into this data store so that as the state of our chain changes and data kind of moves in and out, we can simultaneously know natively in our data store how many different tip sets, how many different chains are using a certain key. And once something gets rolled out, it would be great to immediately mark it for deletion and have different ways to more optimally clean that up. Another really important call out is that based on how this works using memory map files, we can have multiple processes read the same files and interact simultaneously, read the memory map files and interact simultaneously. So we could have a Go version of this code and simultaneously with some chat GPT queries have a Rust version of this code. And the idea there would be that the Rust FVM is limited a lot performance-wise by changing contexts back into Go and back. And I heard a few people talk about that earlier this week as a known sort of performance issue that we have. So it would be amazing to reduce that and create some more features. And then just rolling things off, I was checking out that Parity, the Ethereum infrastructure group or client, has a very similar implementation, which I just think is a great validation for this idea. And that's available here. There's been discussion at PL around similar ideas. And then lastly, there's a branch here, Micers/GoMap-SEP3 that we can use currently to test things out. Yeah, thanks, and happy to chat.
So can I use that repository to generate a snapshot, or are there any like limitations on Lotus when using your database?
I'm starting to find the answer to that question. Would love for you also to test it out and let me know. I was seeing, and I can't recall which one, but there was a shed command that didn't have the Go map feature built into it. It just kind of recoded, like, I'm going to open Badger and I'm going to... So that's on my list, but otherwise it seems to work well, with the caveat that I haven't looked at how to work with SplitStore. But otherwise, you should be quite able to.
Right. And have you looked at the memory usage of Lotus with your database compared to with Badger?
Yeah. I meant to add that to the benchmark. That was like my just shooting off the hip. My desktop was running at 40% memory usage with Badger and 30% memory usage with this. 32 gigabytes, I think. So yeah, maybe we can do the math later. But
yeah, this is great. How does the like disk footprint compare? We said it's about 2x faster. Is it 2x bigger? Is it 2x smaller? Is it the same?
It's about the same order of magnitude. I think it's possibly a little tiny bit smaller, but generally it should be the same. The way that the slab works, I think I have that somewhere. Yep, is that this is what's written on disk. So we write the key on disk, we write the value on disk, and then again, this could be variable in sizes, but it's small enough, minor enough, the 4 8-byte overhead, in addition to the actual data being stored.
Magic.
So I have many questions. First is, how do you rebuild the index on restart? Do you just like rescan all the whole data store?
Sure. So there's no rebuilding of the index. The index itself is a memory map file.
Yeah, but what happens if I restart my node?
In terms of like losing data, in terms
Yeah.
of data quality, data persistence.
Yeah, like do I need to re-import the snapshot every time I restart?
Well, it's persistent using memory map files.
So the map is memory mapped.
Correct. Yeah.
Oh, okay. And so, okay, so what happens if I kill the process? That's like in some unclean way.
Totally. And thanks for raising this. I considered adding that, and only can, it's my first version of this presentation. Definitely needs to go into the future work idea in terms of this. Definitely it's completely possible to fully rebuild the map from the slab. But I want to add the Intel's atomic copies over, but there's also a disk sync question with that. But I think generally that warrants further explanation, further exploration, and considering, does that tend to work? Does that tend not to work? And all those things.
Yeah, because like my intuition is that if you have a memory map hash map, you will have a massive write amplification, just coming from the fact that disk drives just are unable to write less than 4 kilobyte blocks. Like they have to write in 4 kilobyte blocks. That's why LSMs are a thing. I think the rescanning on restart is reasonable. Like if your node takes some time, like some minutes to start up, that's not the end of the world. But yeah, like I do think that it would be good to have some. Well, it's necessary to have some strategy to restart after unclean shutdown.
Yeah,
Because
I
that's
think
like literally 100% of complaints about Badger instability come from the fact that Badger used to be very bad at this and still isn't perfect.
Cool. So what's fun is that when we do, let me just go to the benchmark slide. So this, so when we run sort of import chain and halt after import, it takes these 7 minutes to import all the data. The most recent resize, when it logs it out to the console, takes 3 seconds. And so that's a full rewrite of the hashmap index. So because in the hashmap index, we're only storing, 8 bytes per entry, it's very fast in order to write and rebuild that index. And since all the actual data is just stored linearly on disk, that's also really easy to scan. So I haven't investigated the how do we really break this and how do we harden it and whatever, all the fun things that go along with that. I'm really optimistic and excited about, one, that it is really easy to rebuild the index, and two, that things already are working really quickly. So whatever Badger is doing or not doing, that should make LSM writes faster, it's not doing. So we're already kind of beating our intuition on that.
Yeah, I think like being faster. Okay, yeah.
Thank you.
Okay, so I think being faster is like it may come from the lack of robustness or like very optimistic robustness, let's say, because Badger used to be way faster before it could actually survive restarts properly. So yeah, like I'm cautiously optimistic. And also one note about variants. So variants are very, very, very slow. Please don't use them because they are ridiculously slow.
No, thank you. Would love to keep talking. And also, it may be possible that this lands in, if you want full robustness, stick with Badger. We can quantify what the trade-off is and the speed performance is and offer this to people and let people choose.
Yeah. I mean, like you can rebuild most of that data anyway, so.
Awesome.
We have time. One short
It's up to David.
yeah, going back to the benchmarking where you importing a chain. With Badger it takes like over 12 minutes. With GoMap less than 7 minutes. Is that because of like Badger being like is that because of the read amplification, or is it just because of like Badger having this overhead of like built in, which this implementation doesn't have? And maybe follow-up question to that is like, what is the like potential gap if we would say that IO is free, it's instant, like what like is this work kind of like 90% of the potential gain, or is that do we still have like more potential when it comes to IO here?
Awesome. So I just really quickly and want to respect the overall track, just concise answer. There's compaction that Badger seems to do after it's declared, hey, congratulations, I'm done importing your data. And so it seems like Badger's done, then it like goes and does a bunch of stuff for a while. So that seems a lot like where the slowdown is. Gotcha. Well, I just want to, and now not go too long. So that maybe I know, maybe I don't know, but it should be head to head because both GoMap and Badger are doing the same thing. The hashmap should be much more fast for reads, and then there definitely are still juice on the vine in terms of optimization. Just in terms of here, that for one, we're hashing things a few too many times in my implementation, and that's one thing I want to speed up. So thanks.